Welcome back to another beautiful day of CCNA 1. Now we're on Chapter 4, Network Access. This is a big one, as we kind of talked about in the last chapter. This is our TCP/IP layer that includes both, if we were going to the OSI, it'd be Layer 1 and Layer 2. So we're going to be talking about all kinds of things today. Layer 2 addresses, and also how to make cables, and a lot of the aspects of these physical cables. So I'll just go over this. Upon completion of this chapter, we should be able to identify device connectivity options, describe the purpose and functions of the physical layer in the network, describe the basic principles of the physical layer standards, identify the basic characteristics of copper cabling, build a UTP cable used in Ethernet networks, describe fiber optic cabling and its main advantages over media, describe wireless media, select appropriate media for a given requirement, and connect devices, describe the purpose and function of the data link layer in preparing communication for transmission on a specific data or specific media, describe the layer 2 frame structure and identify generic fields, identify several sources for the protocols and standards used by the data link layer, compare the functions of the logical topologies and physical topologies, describe basic characteristics of media access control methods on WAN topologies, describe the basic characteristics of media access control methods on LAN topologies, describe the characteristics and functions of the data link frame. Okay, so basically, just by reading that, you know this is going to be a long chapter, so you might want to break this one up so that you are still paying attention to what we are talking about. Alright, so we're going to jump straight into a little briefing on our home router, and we've talked about this before, right? And the reason they're talking about this is it's doing all three things. So this would be our WAN connection at home to the internet, right? What's taking us across geographical areas? Well, hopefully it's that button, and maybe yours doesn't say internet, but one of them. This is a Cisco Linksys router. Usually says internet. Then we have our Ethernet ports that are like a switch. Inside we have a wireless access point built in. So that's our home router, and in the classroom we're going to have to program all of those things. And why do we do that? Why don't we just have an integrated services router like this? Because when our data scales, this little device's CPU could not keep up. So anyways, I hope you figured out that this is how you connect a cable to your laptop. Oh wow, this is great stuff here. We're gonna keep going on. Okay, so maybe you've heard me say NIC before, and that's what a network interface card is. And so when I say NIC, it either means if I say wireless NIC, we're doing wireless. If we're plugging in, like the last picture, that's still a NIC. So a NIC is any adapter you have that is going to give you networking. So definition up there at the very top, we see network interface cards connect a device to the network. But yeah, from now on we'll just call them NICs, because network interface card takes longer to say. So this is one of our first acronyms. Alright, so now we're getting into the good stuff. The purpose of the physical layer, okay? Well, these are our purposes for the physical layer, except I wouldn't say this top one is. The user data is segmented by the transport layer, placed into packets by the network layer, and further encapsulated as frames by the data link layer. And so that's where we hit data link. So we're going into frames, and that's what this is showing is. So if we start at the source, I don't know, we say, hey, Internet Explorer, we want to go to CCNA, or we want to go to netacademy.com. So it starts out and it encapsulates all that application layer data as it goes down through the 7-layer process. And then the transport layer is going to segment out these big pieces of networking, cut them into segments. Those segments go into network packets. So the network packets feeds it to the NIC, right? And the NIC is, we hit the data link layer, and so it's going to make those into frames and then send it onto the physical layer where we have ones and zeros. And so you can see that right here, right? And so these frames are actually what's being transferred across the network. All of this is happening on the local host, right? After they get these ones and zeros and get the frames, okay? And we'll find out how these frames work a little more as we go on. But maybe it tells us here. The physical layer encodes the frames and creates the electrical, optical, or radio wave signals that represent the bits in each frame. These signals are then sent on the media one at a time. The destination node physical layer retrieves these individual signals from the media, restores them into their bit representation, and passes the bits up to the data link layer as a complete frame. And then it goes inverse. So that is all we're going to learn in this entire CCNA 1. That's all it's about. So if you can just understand that right now, I guess we're good to go. Physical layer media. Alright, so we've talked about this before. We have 3 types. Copper cable, which sends electrical signals, and those electrical signals look like this. Alright, and so how that's going to work is, depending on how we set it up, this is either going to represent a 1, and this is going to represent a 0, or this represents a 0, and this represents a 1. Alright, and so that's how we're getting that. Same with our light frequencies. Each one of these represents a 1 or a 0 based on the color pattern. The signal, that's fiber optic cable, right? The signals are sent as patterns of light. Then we have our radio signals, and they are also going to decode into 1s and 0s, as you can see right here, right? Here's our digital signal. It's kind of showing you when we have a high wave, we're gonna say 1, 0, and it's just that easy. Right? Oh, it's just that easy. Actually, it's extremely complicated, and a lot of this stuff we will not even get into, but hopefully you continue your network education to understand it. But it will give you this chapter will give us a lot of good base to study upon. So, physical layer standards, right? Well, who's implementing them? Some of these standards organizations that we have seen in the past. ISO, remember they invented the OSI model. EIA, TIA, I think this is ITUT, that's how I pronounce it, ANSI, and the IEEE. Okay, and so what are they doing? They're doing different standards based on like ITUT is usually phone lines, and so if it's fiber optic, if it's wireless, like IEEE, we're going to see as Ethernet and the wireless signals, and so they're doing different standardizations. ANSI, in my experience, they're doing different encapsulation mechanisms, and so just different stuff that we will kind of see as we start programming stuff in the future classes, but they just want you to learn about them right now. Alright, and so if we click here, it actually gives us what they're making. So adopting RJ11 connectors are phone connectors, RJ45s are our data connectors that we use. So RJ11 only has 2-pair wire, RJ45 has 4-pair, so 4 wires or 8 wires. Anyways, feel free to look at that. Probably the most important to notice is 802.3, Ethernet, 802.11, wireless, 802.15, Bluetooth. They will ask you that. And now remember, 802.16 is actually our WiMAX or LTE. Alright, so here we go. The fun stuff of electrical encoding. And And so I'm going to warn you right now, I think a lot of this stuff is very confusing when we go into this encoding. But anyway, so physical components, we can look over here. It says UTP, which we're going to find out what that is. This is all copper cable. We have coax, connectors, NICs, ports, and interfaces. What do you do? I mean, we could probably figure that out, especially after we talk about cabling in the future. So here, this is, don't worry, this is probably the only time you're ever going to see this. Do more research on it if it interests you, but you also might want to be like an electrical engineer or something like that if you really like this stuff. So, Manchester encoding. A 0 is represented by a high to low voltage transition, and a 1 is represented as a low to high voltage transition. That's basically just what I was telling you in the last page. This type of encoding is used in older versions of Ethernet, RFD, and near-field communication. Non-return to 0. This is a common means of encoding data that has two states termed 0 and 1, and no neutral or rest position. A 0 may be represented by one voltage level on the media, and a 1 might be represented by a different voltage on the media. Okay, so that's where both of these things are doing a similar encoding, where something is it's going to be negotiated, and we understand what 1s and 0s are going to be. And so they say, hey, faster medias have different encoding, but it's beyond that. Alright, so signaling. So we're going to talk about, we've kind of talked about this before, asynchronous data signals are transmitted without an associated clock signal. Oh, I guess this isn't asynchronous as in DSL. This is on our clock rates of our copper cabling. So this is how we figure out this, where are 1s and 0s. So, yeah, where were we at? Data signals are transmitted without an associated clock signal. The time spacing between data characters or blocks may be of arbitrary duration, meaning the spacing is not standardized. Therefore, frames require a start and stop indicator flag. Okay, and then we have synchronous connections, which are typically like T1 in phones. So asynchronous, I would say this would be probably our Ethernet standards and that kind of thing, or our UTP or coax. They're probably not getting a clock signal. So synchronous, a data signal is sent along with a clock signal which occurs evenly spaced time durations referred to as bit time. So it tells you where your, it gives you a clock rate to tell you where your 1s and 0s should be, I guess. Yeah. I know it's confusing. I'm definitely not an expert on the physical layer, but that's the best I can do right here. We will see some, as we start using these technologies, hopefully they make sense. Alright, so now we're going to go to a term of bandwidth, and I'm sure you've heard this term before, but what does bandwidth actually mean? Okay, so bandwidth, our fundamental of bandwidth, right, is bits per second, which not good anymore, right? Or I guess we could say bandwidth is the capacity of a medium to carry data, and so how fast is it carrying data, or how much data is it carrying? And so that's what bandwidth is. So we have bits per second, right, and then kilobytes. Right now we're on megs. Gigs is great. I would love to see terabytes per second. That would be wild. So these are different bandwidth speeds, and it's always per second, right? Moving on, throughput. Alright, so throughput is, we have a bandwidth, but the throughput is basically the true measure. So we have, our Cable One sells us 100 meg, right? But the thing is that's 100 meg. Usually, if everything is going great and dandy, or how close we are to the ISP, those kinds of things, which is what it's talking about here. The amount of traffic on the network affects our throughput, because this is the actual speed we're getting to somewhere. And it's not just our ISP's traffic. If we're going to, I don't know, say we're going to Google in Kansas, well, how many other people are going to Google, Kansas, and the lines that we share, how much traffic is on there, okay? And then it also depends, what if we were routing to Seattle before we go to this Kansas, or a lot of places in Lewiston, they first route to Chicago, and so then it's sent back. And so that's actually called latency. The latency is created by the number of network devices encountered between the source and destination. So we could have 800 meg, but if we still have high latency, we're going to get a lower throughput than that. And the type of traffic, the reason they say that is, as we've talked about before, like there's a lot of voice and video going over. It's going to take up more network resources along the entire path to Google or wherever we're going, California, Seattle, somewhere like that. And so what we're showing here is probably this person has something like a 100 meg connection, and their throughput is actually, they're only getting an 80 meg download and an upload of 8, which, remember, we call that an asynchronous connection. And to test this throughput, if you guys ever want to, probably the best is known as the Ookla speed test, and you want to make sure you pick your servers, and I'd pick somewhere like Seattle, San Diego, I don't know, New York, somewhere where you think there is probably a data center that you're going to really test your throughput. And that's speedtest.net, and I'm sorry, it's really bad writing, but yeah, speedtest.net. Little flash icon, and you want to pick your server, and then you're good to go. Alright, types of physical media. Well, what are they? We're talking about copper here. Type of copper cabling used. Bandwidth example standards for copper media are defined for the type of cabling used, the bandwidth of the communication, the type of connectors used, the pinout and color codes, maximum distance of media. Alright, so what they're saying is we're going to pick cabling for certain reasons. Such as we talked about before, right? We're going to pick for these management. One of these is a console cable, and that console is going to go over serial, and so serial has a clock rate, and so we have to set the clock rate for it to work. That's one of the reasons. And then over here, and it's going to be really slow too, or it's going to be slower than over here on our fast Ethernet, right? The normal ports that you plug into, these switch ports, these ones are probably going to give you 100 meg or a gigabit, and then I don't know, I guess we could count USB as a copper, but we're not going to. I guess we have gigabit interfaces over here that usually form the LAN of this router. So these would feed to the switches. This actually is a virtual switch card on this router. And then here's our SDSL, which would probably be like a RJ11 going into there. Maybe we would hand off to an RJ45, right? But that would be our DSL module, right? And so we're going to talk about all these things, like distance and why we're choosing them, and the pinouts as we go on right here. Probably this next little section here. So characteristics. This is one reason that copper cabling kind of sucks. Is well, it's nice because it's our cheapest form. Well, I guess that'd be debatable for wireless, but it's our cheapest form of pluggable media. And so, but the problem is it gets the stuff called EMI and RFI, and if we were to take a scanner and hold it up to a fluorescent light, you would see this. So EMI and RFI signals distort and corrupt data signals being carried on copper media, potential sources include radio waves and electromagnetic devices such as fluorescent lights or electric motors, as shown in the figure. I don't see the figure, but anyhow, EMI, if we put a power cable, so we never, if we can help it, we don't want to put a power cable next to a Ethernet cable because it's going to cause interference. And so what does that really mean? It just means that we have a chance of having more frame errors. And so when we have a frame error, those frames are going to have to be resent before we can establish our build it into the other layers, build it into packets, build it into segments, and finally get that application data. Then we have crosstalk, and so crosstalk is when we actually stack where our Ethernet cables actually interfere with themselves, right? Because they're sending an electrical signal and they can interfere. And so what this is going to show is this is what happens. This is what we have theoretically if the world was perfect. But we have interference from EMI, RFI, or crosstalk, and it starts going different, and we can actually have ones where we shouldn't have ones and zeros where we shouldn't have zeros, right? And so the frames are established differently. And so now crosstalk is the actual electrical signals feeding of one pair of wires feeding into the other pair. EMI is caused by power cables, and then RFI is caused by fluorescent lights and anything that produces a radio signal. And someday when we're in lab, I would be more than happy to show you how fluorescent lights do this with a toner and sniffer. But it used to be a lot easier in the classroom. Now they're putting LED lights in, and they actually don't cause RFI, so that's great. So we are copper media. So we have typically three types. UTP. This is what we're going to be using in class, and all it is it's this picture right here. So we have a cable, and it's unshielded twisted pair. So it's just a twisted pair. Okay. So then we have shielded twisted pair. It's the same thing, except we have this big metal coil in there. And why do we do that? Well, there's a few reasons. Mostly to block from interference, and it makes the cable a little harder to make as well, but it's to block from interference, or if we're doing wireless access points on a home, sometimes we use this to ground the access point, because an access point actually works as a lightning rod, and if you don't ground it correctly, lightning's going to shoot that, and if it's going into your router, it's going to fry your router. If it's going directly into your computer, it could just blow every capacitor in that computer up. So good due diligence for a wireless ISP is to use the shielding as a grounding mechanism. Then we have coax, right, which we usually see. Coax is used more with audio, video, or with cable internet. It's fairly easy to make, but we won't make it in class. This UTP cables, you'll probably make so many while you're in this program that I guarantee you'll never want to make one again, but you'll be good at it. Okay. So here is the UTP. Okay, so we have the outer jacket, and then we have the twisted pair. Now, why would we twist the pair? Well, this twist, the more twists we have, why we twist it is because we're trying to stop that crosstalk that is happening. So we twist all the cables together in the wire so that they, instead of causing interference, they actually do the opposite. They're twisted so that the interference actually boosts the signal or protects the signal in the wire rather than causing interference. And then we have an insulator, right, with each color pair. And the reason they're colored is, we'll soon find out, is so we can build cables, right? So we can identify which little wire this is on one side and on the other. And sometimes these cables are solid white next to the orange, like they're just solid white on each one of these colors. And sometimes they're orange and white, green and white, blue and white. Brown and white. That's brown, even though it looks black. Okay. So now we have shielded UTP. All right. So this is what makes STP harder to make. Is you have the jacket, and then we have this braided foil. So you got to cut through that, and then the foil shields, and then we have the twisted pair. And sometimes we don't have the foil shield. Sometimes it's just twisted pair. It depends on how fancy, how much you want to pay for your cable. But if we were really concerned on protecting this cable, yeah, we would do this high grade to do that with those foil shields. So STP cable shields entire bundle of wires with foil, eliminating virtually all interference. STP cable shields the entire bundle of wires as well as the individual wire pairs with foil, eliminating all interference. So I don't know why they say that twice, but they do. Alright, so now we have coax cable. Alright, and you have these different type of coax ends that goes on, that go on very easily. Basically all you do, as I said, we won't be making these, but it's basically a crimping mechanism that you just put these little pieces on, you cut out this copper wire a little bit, and you get the this outer jacket is right here, this braided copper shielding. It works as the second receiver, I believe, and so you get these things aligned, crimp them down, and it works. They're very, very easy cables to make. Alright, so a copper insulator or copper conductor used to transmit the electrical signals. The copper conductor is surrounded by a layer of flexible plastic insulation. The insulating materials is surrounded by a woven copper braid and metallic foil that acts as a second wire in a circuit and as a shield for the inner conductor. This second layer or shield also reduces the amount of outside electromagnetic interference. The entire cable is covered with a cable jacket to protect it from minor physical damage. Okay, so that's coax. Alright, so copper cabling. What are we talking about? Alright, so this is kind of a silly, well, the separation of data and electrical power cabling must comply with safety codes. Okay, so what they're saying is you can't run, there's certain cabling, you can't run Ethernet with power cables, but you wouldn't want to anyways, because like I said before, one, it causes a fire hazard or electrical hazard, and two, it would cause tons of interference in your cabling. Here's our oxymoron. Cabling must be connected correctly. What in life is connected incorrectly and works? So what it's saying is we're going to learn that you can make different types of cables, like there's straight through, crossover, and rolled. And so that's what we'll be talking about here in a few moments. Installation must be inspected for damage on these cables, as you will find out if we can bend them too much and they break, or we can pull the entire cable out of the RJ45 connector if we don't have them crimped enough, or we can crimp them too much where they just break completely and won't work. And the equipment must be grounded. If your equipment's not grounded and you touch one of these switches, it'll give you a little shock. Most of these switches don't have enough to really hurt you, but it's surprising, and for the equipment and for yourself, you want to make sure that they are grounded. Alright, so we have a little activity. Feel free to do that. Properties of UTP. Alright. So, cancellation. Designers now pair wires in a circuit. When two wires in an electrical circuit are placed close together, their magnetic fields are the exact opposite of each other. Therefore, the two magnetic fields cancel each other out and also cancel out any outside EMI and RFI. So, that has to do with the twisting and how they are paired, how they're rolled inside this cable. Then we have varying the number of twists per wire. To further enhance the cancellation effect of paired circuit wires, designers vary the number of twists of each pair of in a cable of UTP cable must follow precise specifications governing how many twists or braids are permitted per meter of cable. Notice in the figure that the orange and white pairs are twisted less than the blue and white pair. Each color pair is twisted in a different number of times. Okay, so that's just to avoid cancellation as well. Alright. So cabling standards. Alright. So if we see this older version is Cat 3. Alright, so this was what we use for phones. You can transfer data on it. You have a lot of frame errors when you do, because as we can see, it's not twisted. It's just straight. We don't have these twists to make up for it. So then we have Cat 5, Cat 5e, most common, right? We can go over it. We can go up to a gig on it. It's not recommended, but we can do it if we want to. Or I guess that's just Cat 5. So Cat 5e that's all the wire that we have. Unless you're using older cables that have been made, everything in the class is 5e. Then we do have Cat 6, and if you really want to make a cable that is frustrating, Cat 6 is very frustrating. But as you can see, what's cool about it, you can do 10 gig, even though it's not recommended. So here's the question: if it's not recommended, what can we do 10 gig on that is recommended? Well, that's fiber optic. Fiber optic is always our faster. Alright, so now we have connectors for the Cat 5, and we've been talking about these in, what is this, a video? So anyways, we have RJ45s, and they look like this, right? And then they plug into these sockets, and I'm sure you've seen these before, and I actually hate the socket that they're showing here. This is the worst one to punch down, but anyhow, it works if you have to do it. When we're putting on these connectors, we want to get this jacket in here because, one, this is going to cause it to break, and it also can ruin our wire integrity. Like it's going to cause this cable to go bad fast, but it also can cause interference. Whereas if we want to get that jacket up there, so always cut it a little bit shorter if you're seeing that you can't fit your jacket up there. I try to see where the jacket goes right to where the square goes. You could even go past there if you could force it up there. It's not going to hurt anything. So that's what we're looking for when we have a RJ45 put on here. Alright, so here's our types of cables. And we're going to go over this more, right? But Ethernet straight through cable, and it's the most common because what it does is it connects devices on the same layer, or on different layers, I'm sorry. So usually we take a computer and we plug it into a switch, and so as I've said before, we have a layer 3 device in a computer and we plug it into a switch, and then we have a router and we plug it into a switch. Once again, that's a layer 3 device going into a layer 2 device, and so we need a straight through cable. And so the most common type of network cable is commonly used to interconnect a host to a switch and a switch to a router, just as I said, but it just uses anything that is on a different layer. It will work. And we'll find out why, because it's how the NICs transmit data. But we have two categories of cabling that we can do, and so all this is a standardization. It'd have to be a really old building to use it. Most places use B, and that's the standard now. But to make a crossover, which is our next cable, we actually have an AN and a BN, and that makes a crossover end. Okay, so it says an uncommon cable used to interconnect similar devices together. For example, a switch to a switch, or a host to a host, or a router to a router. But the reason it's uncommon is because in newer technologies we don't actually have to make these cables, but our switches in the classroom, most of them don't support that newer technology. So when we're working in the classroom, you have to make straight throughs where you need them and a crossover where you need it. Okay, then finally we have this rollover cable, also known as a rolled cable. It's a Cisco proprietary cable used to connect a router or switch console port. Which, what this is we have a serial adapter that we plug into, and we use this rolled cable. You will probably not have to use well, you might have to make one of these, and it has its own special end. One end has to be this straight through either A or B, and then the other end is actually rolled, and so it's just this inversed, right? So these aren't inversed. What's switched on our A and our B, maybe you guys noticed, is the green and the orange, right? So on the B, it starts out with orange, and then in the middle, the pair 3 separates the blue, whereas on A, the green starts out, and then the orange separates the blue. Other than that, they're the same. On a rolled cable, it would be the brown would start. It would go brown, white, green, blue, white, blue, green, white, orange, white, right? So the exact inverse, and so we would just inverse it, so it's just rolled over. And so we can actually just build this cable again, and we put the RJ45 on backwards, and that makes us a rolled cable. And I'm sure somebody will be making a straight through cable and accidentally make a rolled cable. It happens all the time. Testing UTP cables. We have some tools. We can use wire maps. We can use testers that will wire map. They'll tell us the cable length, tell us signal loss or crosstalk, and I will show you guys that if you come in for labs. So, cable pinouts. Alright, I suggest you guys do this because I will test you on your cable pinouts. It's something you need to know while you do this class, because there will be quite a few test questions, probably even on your CCNA, definitely on your CCENT, and it'll ask, hey, this color coordination, is it straight through, is it a B, is it a crossover, what is this? So why don't you guys make sure you take a look at this and build some cables on this activity, or I guess this activity right here, 4226. Great idea. So we're moving on to fiber optic. Alright, so we've kind of talked about fiber optic before, and this is a 10 gig cable that they're showing. 10 gig still uses a older standard, which we'll talk about soon. So where's fiber optic being used? Enterprise networks, right? Fiber is the backbone cabling of applications and interconnecting infrastructure devices, right? So what we call our core and distribution switches are probably all connected with fiber optic, is what it's saying. It's used for fiber to home, which is just super high speed to the home, usually pretty expensive to get. Long haul networks. We use fiber optic because it can go much further. So service providers use long haul terrestrial optic fiber networks to connect countries and cities. Networks typically range from a few dozen to a few thousand kilometers and use up to 10 gigabit base systems, and probably more than that actually. Submarine networks. Special fiber cables are used to provide reliable high-speed, high-capacity solutions capable of surviving in harsh undersea environments up to transocean distances, also known as going under the ocean to Britain, or I believe that's where it goes. There's a map here in a second. So, how does the fiber optic cable work? So it has the core, alright, consists of pure glass, and is part of the fiber where light is carried. Okay, well this is on a certain type of copper cable. Okay, the cladding, the glass that surrounds the core and acts as a mirror. The light pulses propagate down the core while the cladding reflects the light pulses. This keeps the light pulses contained in the fiber core in a phenomenon known as total internal reflection. And what's kind of interesting about this is if we really wanted to, if we got into studying fiber optic more, we could put this fiber optic cable in a glass of water and it would actually show us what they're talking about here, because the light would go through the water but it would bounce off the glass of a glass of water. Very interesting. The jacket, typically PVC, protects all the stuff. Alright, so fiber media types. So we either have the light pulses are either transmitted by lasers or LEDs. Okay, so first we have single mode, and single mode is the best. It has a small core right here, and so it's going to be glass. It has less light dispersion, meaning the signal is better. That's why we can go further with single mode. Single mode is full duplex and can go further. Suited for long distance applications. So what I'm saying mean by full duplex is one wire. Oh, you guys don't know what full duplex. It means it can send and receive on one wire at the same time. Alright. Uses lasers as the light force, commonly used with campus backbones for distance of several thousand meters. And kind of this LED stuff we're going to talk about, which is multi-mode fiber. It's cheaper, but the price of single mode has gone down to where it's not used as much. So has a larger core. This is the multi-mode. Allows greater dispersion and therefore loss of signal. So it's only for short range. Suited for long distance applications, but shorter than single mode. Uses LEDs as the light source, commonly used with LAN or distances of a couple hundred meters within a campus network. And that's what I mean, shorter. But because the cost of single mode is cheaper nowadays, I would say you don't see a lot. Multi-mode is kind of being everywhere I have heard of is phasing out multi-mode. Okay, so now we have connectors, and I will give you some test questions on these. Cisco won't. So this is our older ST, right? Here we go. Straight tip, an older bayonet style connector widely used with multi-mode fiber, and I do have some of these in the classroom. And how I remember these is ST. I guess you could remember straight tip, but I call them standard twist, ST, because you twist these on, and so that's how I remember that. Then we have SC connectors, which I remember as square connectors. Their real name is subscriber connector, sometimes referred to as a square connector or standard connector. It is a widely adopted LAN and WAN connector that uses a push-pull mechanism to ensure positive insertion. This connector type is used with multi-mode and single-mode fiber. And on our LAN switches, it's being phased out. I believe it's still used for 10 gig quite often, but this is an SC connector, and it requires a GBIC interface to go into, which I believe they will show us that in a second. Then we have our LC connectors, which I remember by saying little connectors. LC connectors, little connectors. And so we have single mode and multi-mode LC connectors. This is the new standard. All of our newer Cisco switches are going to run what's called an SFP, a small form pluggable, and that means that they support LC connectors. Alright, whereas our GBIC interface, gigabit interface cards on our older switches in the classroom support SC connectors. Alright, so sometimes called little or local connector, is quickly growing in popularity to its smaller size. It is used with single mode fiber and also supports multi-mode fiber. Personally, I like SC connectors a lot more than LC connectors. LC connectors are small, and so you can fit more in there, but they're also very easy to pull out. And so if you have some tight cables and you are trying to find the end of a cable, pull on it, it's very easy to pull these LC connectors out, whereas the SC connectors are in there a little better in my experience. So alright, so we will not be terminating fiber optic in here, but maybe if some of you guys work for Schweitzer Engineering, they do terminate fiber cables, but the reason we don't is it's glass, and so you have a chance of getting cut, and also, as you'll find out, like our RJ45 ends cost, I don't know, 20 cents to 10 cents probably a piece when we buy them in a lot, whereas these fiber connectors are more like $10 a piece, and so it costs too much for us to terminate fiber. So what are some causes for errors in fiber optic? Basically, when we terminate a fiber optic, it's simpler than copper. You have these measuring tools, you cut them out, you cut certain parts of the cable, right, the cladding and the core out to a certain length. You have a little measurement thing, and then it just kind of smashes it, smashes the end on there, and it either works or it doesn't. And so if it doesn't work, these are what we're looking for. Misalignment. The fiber optic media are not precisely aligned to one another when they joined. End gap. The media does not completely touch at the splice or connection, and this is why we measure them out, and it's so important. End fission. End fission. The media ends are not well polished, or dirt is present on the termination. So we always polish fiber. In fact, our fiber optic cable, just the SC ends that are uncovered, if we were that is a sin in a network environment that actually is using them for business applications, because that can actually cause frame errors, just them being exposed to little bits of dust. Typically, you pull off the end caps, and then you polish even the end caps, and then put them in when you do these fiber optic connections. So, fiber versus copper. Why don't we just use fiber everywhere? Because it's awesome. Well, there's some. It's more expensive. It takes different skills and equipment required to terminate and splice cable infrastructure, more carefully handling the copper, right? That polishing and all that. But really, different skills and equipment. It's not any harder. It's probably, I don't know. In ways it's easier, in ways it's harder. It just costs more to put the ends on, I guess. So I would say the biggest reason we don't use it is cost. But here's the difference. All right, so our UTP cabling can only go 100 meters or 300 feet, right? It supports 10 meg to 10 gig, right? Where we have bandwidth on our fiber, 10 meg to 100 gig. That's a big seller, probably right there. Then here's our second one. Remember, we have the short distance, 100 meters. This can go 10,000, right? 10,000 meters. Immunity to EMI and RFI. It is not immune to EMI and RFI. It is very easy to have interference. The light doesn't care. You can throw this thing on a power line. It does not care. It's light, so it's not worried about electrical signal. Immunity to electrical hazards. Well, guess what? Copper cabling passes electrical signals, so it's possible, I guess, you could get electrocuted, or electrical signals could go into your cabling and actually light your jackets on fire. I guess that's what they say. I myself have never seen anything like that, but it could happen. Now, light doesn't care. It's not, glass doesn't conduct electricity, so we're okay there. Media connector costs. Oh, here's where it changes. Low, expensive. Installation skills required. It says low and high. Well, I guess. I have installed a little bit of fiber, and I didn't think the skills were much more complicated. Safety precautions. Well, like I said, this is glass. You also have lasers to blind you. What else? The glue a lot of times that you had to use in the past was toxic. So yeah, that's where the safety precautions here is probably why they're saying it's higher. Okay, and that's also why we don't make them in class. Okay. Now we're on to wireless. Okay. Well, we'll go over what do we have. Wireless does have some areas of concern, including wireless data communication, the convergence area, or coverage area, sorry. Wireless data communication technologies work well in open environments. However, certain construction materials used in buildings and structures and local terrains will limit the effective coverage. Okay, so what they're saying is actually this is why wireless, we love wireless, but it has a lot of problems because wireless doesn't like metal. It doesn't like water. It doesn't like wood. It doesn't like people who are made out of water. It doesn't like long hallways. It doesn't like reflective and what I say about it doesn't like, this is all stuff that will cut down. And so we have different frequencies, and that's what we're going to be talking about. But the reason we can't use 5 gigahertz signal, if you use this in your home and you're not in line of sight with your device, you know what I'm talking about. Your 2.4 gigahertz is going to be, it's going to go through walls easier because it's a smaller scale. Because as we've talked about, or I guess we haven't talked about this, different class. So we've kind of seen waves, and so wireless waves, if we're at 2.4, we're going to say that we're going like this, and so this wave can go through. Whereas if we're at 5 gigahertz, our wave is like this, and it's easier to distort. And so it's great and faster if we can see it and it doesn't go through any walls, but in most scenarios that doesn't work that way. And then other things that block wireless, so if we're talking about landscapes, trees and all these things that, right, a tree has leaves that has, it's sucking up water, and so it causes interference. So you might have really good wireless signal in the winter, but then in the summer when the leaves come back, you probably don't, or you might not. So then wireless is susceptible to interference that can be disrupted by such common devices as household cordless phones, some types of fluorescent lights, microwave ovens, and other wireless communications. And so this is actually 2.4 can be a lot of cell phones actually, or a lot of cordless phones run on the 2.4 gigahertz, and so it can knock your 2.4 gigahertz off. Same with microwaves and these, and actually other wireless access points cause interference. So other things that degrade your signal and security, right? Because you don't plug into it, anyone can come over and access your wireless network. Even if you password it right, there's a chance they could password crack it. Even if you hide it, if you think hiding your SSID is a good idea, it's not. You can actually bypass all security through a, I want to say, through a wireless frame. If you're hiding it, you can actually bypass the security if you know what you're doing. And probably the people that are trying to steal your information know what they're doing. So a lot of times it's better to actually not hide your SSID and just have people show it to the world and keep a strong password with strong encryption on there. But that'll be stuff you'll learn about later in CCNA, and I am sure security as well. So our wireless standards. I've kind of talked about these already. So this Wi-Fi, which we'll talk about what that means in a few, but 802.11. All right, so we have A, C, or A, B, G, N, AC, AD. All right, so AD is the newest. It's not actually ratified as far as I know. But as you can see, it shows us the speeds here and what frequencies it runs on. If you're interested in this, I can talk to you more about it. Send me an email or start a discussion, and I can talk more on the wireless. it uses this thing called CSMA CA, which is carrier sense. Multi-access collision avoidance. Sorry about the pause there. And so that's 802.11. So for 802.11.15 is our Bluetooth, and 802.16 is our WiMAX, as I've talked to before, usually used for ISPs. Alright, so 802.15, this Bluetooth, wireless PAN. I don't remember if we talked about a PAN before, but that's a personal area network. So that's smaller than a LAN. That means you have to be close, as probably many of you people know with Bluetooth speakers. If you're not close, you get a lot of interference and it stops working. 802.16, commonly known as worldwide interoperability for microwave access, uses a point-to-multipoint topology, provides wireless broadband access. And so the difference between 802.11 and 802.16 is higher speeds and further distances. We can go non-line of sight and get 25 miles plus probably, and stuff like that. But that's more for wireless ISP information. Anyways, so wireless LAN. So wireless LAN is using 802.11 something, right? And so how do we get a wireless LAN? We have a wireless access point, and then we have a wireless NIC that will connect to that. Wi-Fi standards. So it's going to talk about the A, B, G, N, and AC and AD. Okay, so A was the original. It went out very fast because even though it's faster, as we can see, it's faster than B. It's 54 meg instead of 11 meg. That 5 gigahertz, as I said, you couldn't go very far because of the line of sight. And so B rolled out and basically killed it, because even though you were slower, you could be further away, and that 2.4 gigahertz was great. Then they came to G, and so G could do 54 meg at 2.4 gigahertz, and so it was great. And it was also backward compatible, as you can see, with 802.11b. Why? Because they both worked on the 2.4 gigahertz range. Then we came to N, and N says 600 meg, and this was in the third tier of it, which was not too long ago. It couldn't do this at the start, and you actually have to have multiple radios to get speeds like this in your access point and in your NIC. You have to have multiple antennas and that kind of thing. But anyhow, what was cool about it is it ran both 2.4 and 5 gigahertz. But if you want those higher speeds, you're going to have to go to the 5 gigahertz. The 2.4, I believe it maxed out at like 200 meg is the fastest you can go on there. Then we have AC, which in its next rollout, I don't know if it is to tier 2 yet, but 1.3 gigs. I have it in the classroom. I'm not seeing that. It's 5 gigahertz only, so I think this AD will probably kill it. But it is not that fast yet. But there is this thought that it can be what's called full duplex, which, as I had just said before, you could send and receive at the same time. All these other wireless technologies are half duplex, which means they send and then they wait to send back. The access point waits to send back. And we can talk about that more if you're interested. But then we go to AD, okay? And so AD, 7 gigs supposedly. I've not tested this out. I don't think it's been ratified. So it's not a real, it's not, it's just basically a beta test to this point, but it runs on 2.4, 5 gigs, and 60 gigs, right? And it's backwards compatible with everything. I guarantee this is probably full duplex, especially if we're getting 7 gigs, but it's very cool for wireless ISPs and home networks if we're actually getting that kind of speed, because that means we can start offering a lot higher speeds through wireless. Okay, if you guys are more interested, feel free to look through some of this wireless information. There's a chapter in, I believe, CCNA 4 that is completely about wireless. Okay, so there's the first hour. So if you're still listening, I would take a break, because now we're going to go into, that was basically layer 1 stuff. Now we're going into layer 2, so the TCP IP network access layer is equivalent of the OSI model of layer 2 and layer 1. So we talked about layer 1, now we're going into layer 2. And so the major tasks of the data link layer are, it accepts layer 3 packets and packages them into data units called frames. It controls media access, control, and performs error detection. And so what we were talking about before, right, that had to do with ones and zeros and how it was encoded and the type of, was it coming through light, wireless, or electrical signal, right? Radio signal, electrical signal, something like that. So the data link layer is broke into, it has 2, and I'm going to go over these fairly quickly because we have a whole nother chapter on the Ethernet layer which talks about these again. So we have the LLC, the logical link control, and the media access control. And basically, as we can see in this picture, the media access, it handles the hardware. It is saying, hey, we can use any technology. Otherwise, Ethernet, or not Ethernet, any technology you're using, you would have to say, hey, you can only use this type of cable. But this allows us to use Ethernet, Wi-Fi, Bluetooth, whatever. We can network because of the MAC sublayer of the data link layer. All right, and then the LLC is our drivers. It's the software that provides. It's our network drivers basically. So, and it handles the stuff from the network layer, whereas the MAC handles the stuff from the physical layer. All right. So let's get into this. The LLC. This is the upper sublayer, defines the software processes that provide services to the network layer protocols. It places information in the frame that identifies which network layer protocol is being used for the frame. This information allows multiple layer 3 protocols such as IP version 4 and IP version 6 to utilize the same network interface and media. So then we go to media access control. This lower sublayer defines the media access processes performed by the hardware. It provides data link layer addressing and delimiting of data according to the physical signaling requirements of the medium and the type of data link layer protocol in use. Alright, so what it's saying is we can use wireless and what I just said. We can use Ethernet, wireless, Bluetooth, WiMAX, whatever. This is what's allowing us to do that. So, here's our section on media access control. So, MAC. Maybe you guys have heard of MAC address before. I talked about it, I think, in the last chapter. It's our layer 2 address. So if you remember how ARP works, we need that layer 2 address, and that's called the MAC address. It's also called the physical address, or the hardware address, the burnt-in address. And even though it is the one built in, it is our physical address, meaning we don't program this. But it's the one stripped away as we traverse through different networks. Maybe you recall that from the last chapter. So here's a little something on our frames, I guess. It's going to show us the different ways that things traverse, right? So we probably started out with Ethernet, now we're going through satellite, right? And now we're going to go through wireless to Japan, and that's the that's what the MAC allows all of these different types of media to be used without interruption. All right. So, the purpose of the MAC, is that what we're saying? Alright, I guess what it's saying is that the what the router does as it goes along the way is we're changing these frame addresses as these frames are sent along the wire. So the router looks at the packet and it changes the frame encapsulation, and it's allowed to do that because of the MAC layer, or media access layer. Okay. All right. So frame structure. Right. So at our layer 2 that's getting sent across, it has this frame header, which is giving us all of the frame information about the stuff inside. You know, how many frames we're going to receive to build our packet, which will be converted into our segments, right? Which will have our application layer data and finally get to the application. And so then we have our trailer, and our trailer is error checking to make sure the frames that we are receiving are not damaged in the process. So we've talked about, you know, we're going to have to resend frames if they're damaged from interference. How do we tell if this interference? The trailer has that error checking information, and so the data link layer, I'm just going to read you this right here. Data link layer protocols require control information to enable the protocols to function. Control information typically answers which nodes are in communication with each other, right? That'd be our source and destination MAC. When does communication begin? Communication between individual nodes begin, and when does it end? Which errors occurred while the nodes are communicated? Was there interference, or did this frame get damaged? Which nodes will communicate next? Okay, so that's media access, and that has to do with probably half duplex, right? So here we go. Here's their definition of the header. I gave you mine. Contains control information such as addressing, and it is located at the beginning of the PDU. And remember, each layer has a protocol data unit. That PDU physical was bits, data link is frames, network is packets, transport is segments, application is data. All right, and so the data. All right, so this is the application, or as we can see, we have the packet, segment, data. A lot of times it's called payload. Contains the IP header, transport layer header, and application data. Right. So this is what's going to be built after that. The trailer contains control information for error detection added to the end of the PDU. Okay, so creating a frame. So this is what is actually in the frame. So in our header, this is what we have. We have a frame start and stop indicator. Okay, so used by the MAC sublayer to identify the beginning and the end limits of a frame. Right. So this is how we're going to get our data, right? It's telling us where the start is and where the stop is going to be. Addressing. These are our MAC addresses or some kind of layer 2 address. It's going to be our MAC address in Ethernet, but it could be other things. Type, used by the LLC to identify the layer 3 protocol. And so that's what it talked about already. Remember, we read that last thing, and it said either IP version 4 or IP version 6. For most of the stuff we're going to do, it's probably going to be IP version 4. Control, identify special flow control devices. And so this would be layer 2 QoS. Data contains the frame payload, i.e. packet header, segment header, and the data. Error detection included after the data to form the trailer. These frame fields are used in error detection, and I think we're going to talk about them in a second. And then the frame stop they don't talk about, but it was identified in the frame start. Probably wouldn't be a bad idea to do the frame activity. So here's our data link layer standards. Remember, we had our physical layer standards, and now we have our data layer. So we're seeing some of the same stuff. Well, actually, IEEE, we have 802.2. That's our LLC that we've been talking about. 802.3 Ethernet. 802.4 token bus legacy. 802.5 token ring legacy. 802.11 talked about that a lot. Wireless. 802.15 Bluetooth. 802.16 WiMAX. These other ITUT is basically phone stuff. ISDN, ASDL, frame relay. The G8100 to 8199 MPLS over transport, ISO HDLC, which has to do with serial, and then this FDDI is a fiber. ANSI is a fiber as well. So I wouldn't kill myself learning these. Just kind of say, oh, I see ITUT. It's probably something to do with phones. IEEE, the things to know: 802.3 Ethernet, right? 802.15 Bluetooth, 802.16 WiMAX, 802.11 wireless. That's probably the most important. Alright, so media access control, we're still there. So what they're saying is, I talked about that CSMA, Carrier Sense Multiple Access for wireless, and it was using CA. But now we're going to talk about wireless and why we need these access technologies. Is if we have multiple people on a network, how do we know when we can send or how we can send, right? And so it's showing us a topology, how the connection between the nodes appear to the data link layer, right? That's the topology. Media sharing, how the nodes share the media. The media sharing can be point-to-point, such as in a WAN connection, or shared, such as in a LAN. And so what that means, if we go back to I'll just show you. So in a LAN, see, all these guys are in a network, and if we were to throw another router in here, and in what we've seen before, I should put in a serial connection, but I'm not going to. I'm going to just put on an Ethernet because I don't have a serial interface in these right now. So I throw that in there, and they're off, of course, but this would be point-to-point, right? This network is just point-to-point. There's only one. If you're sending to this guy, and if this router is sending across this network, he's sending to this router over here. Whereas this, it could be sent in the router, it could be sent to this PC, this switch. You have a lot of, this is a shared media, this is a point-to-point. Physical topologies and logical topologies. Alright, so we kind of talked about these the other day, and I told you that I do a hybrid between the two when I draw stuff. Refers to the physical connections, and it identifies how end devices and infrastructure devices such as routers, switches, and wireless access points are interconnected. Physical topologies are usually point-to-point or star. See Figure 1. Alright. So this would be point-to-point, and this would be star. And what they mean by star is we could make a star where they all connect inside, right? So the network could actually be drawn where, like, so we're going to move all this stuff over so it kind of looks like a star. So we have this router, and now I'm running out of interface. I'm going to have to put something else on here. So if we want to put on an interface, here's a good lesson. We click this power button, and then over here on the side we have module interfaces, and they show them down here. We just drag those modules in to one of our WAN slots, and then we power it back on. Okay, and so now I have two more connectors, and so I can take my routers, and I'm going to throw a couple more in here. I'm actually going to have to power them off and put a module in them as well, so I can do some serial. Oh, it's on. Let's see if it's off now. It looks like it's off. Alright. Okay, here we go. So we go serial to serial. This is that serial connection I was talking about. So these are all point-to-point, but even though they're point to point, because this is a different network, this is a different network, this is a different network, and this is a different network, because each router interface has to be a different network. But you see how that makes a star, where everything is connecting to a central point? That's what they are talking about there. And I close my packet tracer, so that's not great. And then logical refers to the way a network transfers frames from one node to the next. This arrangement consists of virtual connections between the nodes of a network. These logical signal paths are defined by the data link protocols. The logical topology of a point-to-point links is relatively simple, while shared media offers deterministic and non-deterministic media access control methods, which we're going to be talking about what those means in a second. And so this is the logical with all of our IPs and where we know they're gonna send it to here if they get there, but we don't see the switches that they actually go through, right? Anyway, so now we have WAN topologies, and this is gonna go point to point, what we've been talking about. Hub and spoke looks a lot like our star, except it's a WAN. So hub and spoke just means we're connecting to a central point. Then we have full mesh. We could also have partial mesh if all these didn't go to full mesh. Just means that every router goes to every router in the design. It's super expensive, probably never happen. So you have a partial mesh where every router goes to quite a few other routers, typically. Physical topology. Oh, there we go. Point to point. There's more. Oh, well, maybe we're just going to talk about this one. But anyways, we kind of already talked about that point to point. Logical. Okay, so what it's saying for a WAN technology is we don't know what's actually, when we draw a cloud, I think I talked about this, but we don't know what's actually inside the cloud, right? And so point to point, even though, because we're going over other networks, it seems like we're connected just like we were in our physical, right? Where we're actually going through our own network, but we're just connected to each other. This is where we're going over, a service provider over the internet, or WAN, some kind of provider that is, we're connected, but we're connected over long ranges. Alright, so finally we get to duplex. Alright, so half duplex. Both devices can transmit and receive on the media, but cannot do it simultaneously. Ethernet has established arbitration rules for resolving conflicts arising from instances when more than one station attempts to transmit at the same time. Figure 2 shows half duplex communication. So what it's going to do is first it receives, it's got to wait till it thinks it's not busy, and sends. The problem with this is it allows, if we were doing half duplex and we had a whole bunch of stuff sending, we could have a collision on half duplex because it's waiting to send. Then full duplex, right? Both devices can transmit and receive on the media at the same time. The data link layer assumes that the media is available for transmission for both nodes at any time. Alright, so we're going to show that. Bam, see? Oh, it's just so much better. You get higher speeds. This half duplex is usually 10 meg connections. 100 meg, gig, all that stuff's going to be doing full duplex. Alright. Physical LAN topologies. Okay, here we go. Here's our star. Right, okay, so I guess I showed you wrong because I showed you a hub and spoke, because we just have wires in our physical topology. It doesn't actually, they're connected somehow, right? Extended star, they're connected somehow, we don't know. Bus is where we draw this tube, because each person has to talk. Let's see, all end systems are chained together with each other, being terminated from in some form on each end, so each one is terminated. Infrastructure devices such as switches are not required to interconnect the end devices, so these ones we need switches or something. These are these older topologies. Bus topologies were used in legacy Ethernet networks because it was inexpensive to use and easy to set up. But what would happen is if you unchained this computer, the entire thing would break. And same with the ring. So end systems are connected, they're respective. So how this ring works is you talk, and you send to whoever you want, and then it says, okay, now it's your turn. And you talk, and you send to whoever you want, and that's how those work. So end systems are connected to the respected nadir, forming a ring. Unlike bus topology, the ring does not need to be terminated. Ring topologies were used in legacy fiber distributed data interfaces networks. Specifically, FDDI networks employ a second ring for fault tolerance or performance enhancement. Well, I guess it did need to be terminated. I told you guys that. I get them wrong sometimes. Alright, so that's our physical topologies. Now let's see our logical topologies for shared media. Alright, so with shared media we have contention-based and controlled access. So contention-based, all nodes compete for the use of the medium but have a plan if there are collisions. Alright, so what it means is if we have a collision, which means the frames hit each other because everybody's on there, and so we have to resend. If we didn't resend, if it just got into complete chaos, the network crashed. So we have to have a backup plan for what happens. Then we have controlled access. Each node has its own time to use the medium. Alright, so that's what I was talking about with wireless. Is it says, alright, it's your turn, which is actually bad because it's contention based, but anyways, we'll talk about that right now. So contention based uses the CSMA, right? Where this controlled access, I would say that's more like a ring topology, something like that. So in contentious base we use CSMA, and we either use CSMA CD or CSMA CA. And remember, CA was for wireless, and it says that right here. CD is for Ethernet. Okay, stations can transmit at any time. Collisions exist. There are mechanisms to resolve contention for media. So CD stands for collision detection, and CA stands for collision avoidance. Alright. Multi-access topology. Let's see what this video is about. Oh, it's probably just going to show you a collision here. Oh wow, this is a boring video. So anyways, it's showing that E's probably going to send back at the same time that B sends for D. Oh, no, it's not. It detected it, right? Because we have media access control. Great. Alright. So controlled access. Here's our token ring, or our FDDI, right? Only one station transmit at a time. Devices wishing to transmit must wait their turn. No collisions occur, right? Because you have to have the token to pass it. May use a token passing method. So token ring and FDDI. I would guess token bus as well. Ring topology. Well, you guys can watch that. It's similar to what we just saw for the other. Alright. So back to our data link, the frame, and we've already talked about that we have a header, a data, and a trailer. Okay. And I guess it's I don't know. It's showing in a fragile environment, more controls are needed to ensure delivery. The header and the trailer fields are larger, and more control information is needed. All right. So that's when it's raining on your satellite, I guess, and less effort, and you're in a protected environment. We can count on frame arriving at its destination. Fewer controls are needed, resulting in smaller fields and larger frames. And so what it's going to do is we're going to show you the header and probably some different types of frames. So we've already kind of talked about this. We have the start frame, the source and destination, and the type field. We have a layer 2 address. Okay, so our layer 2 address depends on, as we'll see, it'll be different, but usually there's a source and destination. Then a trailer is using, this is a good one. A transmitting node creates a logical summary of its contents of the frame. This is how we're figuring out if it's bad. This is known as the cyclic redundancy check, CRC. So right there, cyclic redundancy check, CRC value. This value is placed in the frame check sequence field of the frame to represent the contents of the frame. So the FCS is looking at the CRC to see if the frame is damaged and needs to be resent. And that's what's going on in the trailer. LAN and frames. So what this is going to say is it's showing us that different frames are sent, right? 802.11 frame, and then we have a PPP frame because this is serial, and maybe we're going to use a different protocol like HDLC across this serial, and then frame relay. So that's a different point-to-point. Now we're going back in. We're going into an Ethernet network, and so each one of those had a different frame, right? Different layer 2 tech, or different layer 2 encapsulation, different frame. So here's our Ethernet frame, right? So supports speeds of 10, 100 meg, 1 gig, 10 gig, and 40 gig actually too. So what's it made up of? It has a preamble, a destination, a source, a type, data, and frame check. Okay, so this is the frame header. This is the frame header, right? For, I believe it's the header. Maybe it's everything. Yeah, so it's just the frame itself. Yep, because that's the data. Okay, so it's breaking this up. This first part is the header. These last 4 bytes is the trailer. This is our application data. Alright, so it's showing you the size. So the preamble used for synchronization also contains a delimiter to mark the end of timing information. Alright, then we have the destination address, a 48-bit MAC address for the destination node. The source address, a 48-bit MAC address for the source node, and we're going to talk about those more in the next chapter. The next chapter is all about Ethernet, so we're going to really dive into this stuff. Type, a value to indicate which upper layer protocol will receive the data for the Ethernet process is complete. So that again is IP version 4 or IP version 6. The data payload, this is the PDU, typically an IP version 4 packet that is to be transported over the media. Frame check sequence, a value used to check for damaged frames. Okay, so now we go to our PPP frame, and it's going to be a little different, right? Because PPP stands for point to point, and so we don't have to have we only have to have one address, right? Rather than on our Ethernet, it's shared media, whereas point to point, it's going to be different. So first thing we have is a flag, a single byte that indicates the beginning or end of a frame. The flag field consists of the binary sequence 0111110. Okay, address, a single byte that contains the standard PPP broadcast address. PPP does not assign individual station addresses. Okay, so PPP can be all layer 2. So this is just happening at a layer 2 level, and what it's doing is, the reason it doesn't have to put a source and destination is because if we look back to our point to point, we can only send it one direction. So it's going to send it that direction and see what happens. Then we have a control, a single byte that contains binary sequence 0011, which calls for transmission of user data in an unsequenced frame. Protocol, we're going to identify the protocol. Data, same thing as the last one. And then the FCS is error checking, just like the last ones. So now we go to the big one, 802.11. And it's got all kinds of stuff going on. And so I'll just let you guys read through here. Really, it's similar, right? But there are several types of wireless frames that do, or this wireless frame is going to do different things to control the wireless, and we could have a whole 2-year course on just how wireless works. So we'll just we might actually do a project where we look into each one of these fields a little bit more, have an assignment where we do that. I will let you know in the future. Alright. But that was the different looks of frames, and that was the network access layer. We had layer 1 and layer 2, and we will be seeing more of it as we study layer 3. As always, if you have any questions, post a discussion or send me an email.